Peng from University of Colorado Boulder. It's a pity I cannot attend this conference in person for some family reasons, so I give this presentation through a recording. Michael just mentioned I'm going to talk about ozone production from GUV 222, as previous talks have covered some big pictures for it. I'll talk about it in more detail. This is the experimental setup we have been using to characterize the GUV 222 induced chemistry in the air. We use an environmental chamber, which is a 21 cubic meter Teflon bag. We put the GUV device at the corner of the bag. When the GUV is on, we always keep visible light off in the chamber enclosure. We also use research-grade ozone analyzers and state-of-the-art mass spectrometers to measure gases and aerosols of interest. I'll give more time for devices we decided not to use for gas and aerosol measurements in our experiments. These are low-cost sensors, an electrochemical ozone sensor and the purple air particulate matter sensor. Our tests found electrochemical ozone sensors don't work below 100 ppb ozone. Their readings don't change as the real ozone concentration increases. And purple air sensor we tested don't see SOA particles at typical PM 2.5 mass loadings. They can see a minor fraction at very high PM loadings. This is because they are conceptually optical particle counters using 657 nanometer laser. Usually SOA diameters are 200 to 300 nanometers. They're too small to have lasers scattered and thus detected. For our experiments, ozone measurements are relatively easy with research-grade analyzers, and ozone production is proportional to fluence rate. It's possible to use ozone concentration to determine fluence rate in our Teflon chamber, as ozone losses are very small in such a clean and controlled environment. But we can't use this to determine fluence rate in most indoor environments because ozone losses are also governing its concentration, and the losses are fast and variable there. So I propose CBR4 as a photolytic tracer for the 222 nanometer band fluence rate determination because its absorption peaks near 222 nanometers and it breaks up when it absorbs a photon. And its photolytic decay can be detected with high sensitivity and precision by proton transfer reaction mass spectrometry. Then I'll show some of our chamber experiment results for Far-UV Krypton 36 device, which uses Wuxio B1. We measured its ozone production rate of 21 ppb. During the experiment, we clearly saw ozone production stop when the lamp was off. Ozone was stable during the lamp off periods. This is unlike Michael's experiments in a steel chamber. We also measured a CBR4 photolysis rate of 0.093 per hour for this Wuxio B1, and we have the ratio between them, 230 ppb. This can be regarded as a characteristic of a GUV 222 lamp. We have another device with Wuxio B1. Its ozone production rate is slightly higher, and CBR4 photolysis rate also slightly higher. And its ratio between these two is still 230 ppb. And as you know, NIST measured the emission spectrum of an Wuxio B1 with literature absorption cross-section and the quantum yields of O2. We can calculate the O3 production rate of this Wuxio B1 at a certain fluence rate. We can also calculate its CBR4 photolysis rate, and the ratio between them is again 230 ppb. This gives confidence in our characterization. The unfiltered krypton chloride excimer lamp emissions also include a band peaked around 190 nanometers. O2 cross-sections around 190 are about 100 times larger than at 222 nanometers. So the unfiltered 190 nanometer band makes 4 times ozone, but it contributes little to CBr4 decay. So this leads to a ratio between the two rates of about 900 ppb. So if we measure the ratio between the two rates of 230 ppb for an Wuxio B1, we can say its 190 nanometer band is likely very well filtered. If the 190 nanometer band is well filtered, we can further assume the same shape of emission spectrum of a lamp as this measured Wuxio B1 to quantify that lamp's fluence rate. Because under this assumption, the fluence rate of a lamp is proportional to its CBr4 photolysis rate. If a fluence rate of 2.1 microwatt per square centimeter is assumed for the next measured Wuxio B1 emission spectrum, it will result in a CBr4 photolysis rate of 0.097 per hour. For the Far-UV device with Wuxio B1, we measured a CBr4 decay rate of 0.093 per hour, corresponding to a fluence rate of 2.0 microwatt per square centimeter. Similarly, we can get the fluence rate of the other Wuxio B1 we have, 2.2 microwatt per square centimeter. We also tested other GUV 222 lamps. Here are the ratios between the two rates. Most lamps have these rates between 200 to 300 ppb, but we observed substantial lamp-to-lamp variation for Eden Park lamps. We tested 2 Eden Park lamps. They are the same type. We call them A and B. And we found a significantly lower ratio between the two rates for Eden Park B than other lamps. We're not sure why. And more surprisingly, the other Eden Park tested showed a very high ratio between the two rates. We think it's likely due to electrical discharge in its housing. I'll explain why. We put an Wuxio B1 and the Eden Park A outside the chamber bag and had them shine toward the bag with filters removed. We could measure a high ozone production rate in the bag for Wuxio B1, but for Eden Park A, the ozone production rate in the bag was close to 0. This means the high ozone production by Eden Park A was not due to GUV light penetrating into the bag. We also used the 2B ozone monitor to sniff just outside the box of Eden Park A and measured 12644 ppb. There was a huge ozone production in the housing, likely due to some undesired electrical discharge. We also put a GUV 222 lamp in a real-world setting to measure its ozone production. This is a 33 cubic meter office with a ventilation rate of 0.6 to 1 ACH. We did 3-hour lamp on-off cycles, and when the lamp was on, we saw on average 6 ppb ozone increase. We can reasonably well reproduce the observed ozone time series using a simple kinetic model. This model considers ozone sources and sinks, including GUV-induced ozone production, outside ozone ventilated in, indoor ozone ventilated out, and other ozone sinks totaling about 1 per hour. The other ozone sinks can be, for example, ozone deposition onto surfaces and the reactions with VOCs, which produce oxygenated VOCs and SOA. We can compare the ozone production we saw in our chamber and office with previous reports in the literature. The literature values are lower by about an order of magnitude or more. There are 3 possible reasons for these large differences. Many past experiments were done in small boxes. Those boxes had small GUV light path lengths, leading to small ozone production rates. Also, a high surface to volume ratio of these small boxes could lead to heavy ozone losses to their walls. Besides, past experiments often use low-cost ozone sensors to measure ozone. I already showed they don't work for less than 100 ppb ozone. I just mentioned a major ozone sink is its reaction with VOC making SOA. We also want our model to simulate relevant SOA formation processes in more detail and in a dynamic way. We include some intermediate products, their partitioning to aerosols, surfaces, and aerosol deposition to surfaces as well. In our chamber, we have done some experiments of ozonolysis of limonene, a major VOC emitted indoors and the main indoor SOA precursor. Here's one experiment. So we had some ozone, and when the UV lamp was on, the ozone increased. It reacted with limonene, causing its decay and SOA formation as well. Our model with dynamic SOA formation can reproduce this time series very well. Then we can use this model to simulate ozone and particulate matter increases relative to lamp off conditions at different ventilation and GUV fluence rates. Here are the results, as well as different exposure limits and typical fluence rate ranges for operation. We can see very high ozone and PM concentrations at the high fluence rates above the ACGIH limit for skin exposure. Very roughly, ozone is proportional to fluence rate and inversely proportional to ventilation rate when it's larger than 3 ACH. PM is roughly inversely proportional to squared ventilation rate, as ventilation reduces both VOC, which is PM precursor, and PM itself. Jose will discuss these plots in more detail in the next talk. Here are the conclusions, but I don't have time to read them out. Thank you for listening to this recorded talk. Sorry for not being able to do Q&A in person. If you have any questions or comments, Jose will take them for me.